The hexadecimal number system is a base 16 number system, which means, so it's base 16, which means it's got 16 symbols, and the symbols or digits are 0 to 9 as normal, and then for 10 we've got A, 11 we've got B, 12 we've got C, 13 we've got D, 14 we've got E, and 15 we've got F. So from 0 to 15 can be represented in the hexadecimal number system using the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Now let's organise this into the placeholder grid as normal. We need to make sure we leave enough room. So it's base 16, so we put our 16 down and to the power 0, and then 16 to the power 1, 16 to the power 2, and 16 to the power 3. We'll leave it at that just now because you'll see that these numbers get really big really quickly. So the 16 to the power 0, what is that? That is the ones column. 16 to the power 1, that is the 16s column. 16 to the power 2 is the 256 column. And 16 to the power 3, which is 16 times 16 times 16, is the 4096 column. 4096's column. So you can see that the numbers are getting really big as the power increases. But it is possible to represent any number using this system. So for instance, if we wanted to represent the number 15, so let me write over here the decimal, and we'll try the number 15 to begin with, and let's see what it looks in hexadecimal. And over here we could put binary just to have a look at all three of them. So 15 in the decimal system, so that's 15 base 10, uses the symbols 1 and 5. In hexadecimal, a 15 is represented by an F base 16, and in binary it can be represented in 4 bits as 1111 base 2. So let's say we want to have a look at another couple of these numbers just to get our head around this, because there's a lot going on here. Let me move that up. Okay, so let's say this time we want to look at the number 35. Now sometimes you'll see it written, instead of using base 10, they'll use dec for decimal, and for hexadecimal they'll use hex instead of 16, and for binary they'll use bin. Right, so just to clear that up with you. Right, so at the moment we're looking at the decimal number 35. Now, how can we represent that in hexadecimal? Well, it doesn't go into the 16 to the power 3 column because it's not, that's too big. The 16 to the power 2 is too big, but 16 to the power 1 is the column that we're wanting to use. But how many 16s are there in 35? So what we need to do to work that out is we need to divide 35 by 16. And if you divide 35 by 16, you get 2 remainder 3. So that means that we put a 2 in the 16 to the power 1 column and a 3 in the 16 to the power 0 column. Now that is not 23, so we need to put, let's just put hex this time. So this is 23 hex. Now, what's the equivalent in binary? I think I'm going to have to move over a wee bit so that we've got more room. So what's the equivalent in binary of this? Can we use 4 bits? No, we can't use 4 bits. So we're going to have to increase that. So how many bits do we actually need for so what have we got? 1, 2, 4, 8, 16, 32. So we actually need 6 bits for this. So we need a 32. And then we don't need an 8, we don't need a 4, but we need a 2 and we need a 1. So let's just add 2 more zeros onto this, which brings us on to, and I'll put bin in here instead of base 2, just to show you the 2 methods. Now, this brings us to the next point. Do you see how for each place value, handily, we can use 4 bits to represent? So for instance, we've used 2 place order columns, and we're using 2 sets of 4 bits to represent it in binary, and that's not by accident. Yeah, you've probably spotted this, because if you look at, let me change my pen colour here, if you split these into, instead of 8 bits, and if you split this into 4 bits, and this is your least significant bit, then you've got the binary number 2, and we've got a 2 here. And if you split this into 4 bits, what we've got here is the binary number 3, and we've got a 3 here. So that's pretty good, and that's why this is how the computer handles the hexadecimal numbers. It actually splits the placeholder columns, or represents the placeholder columns, using 4 binary digits. So from now on, what I'm going to do is, instead of putting the binary over to the right hand side, we'll put the binary above the hexadecimal, and we'll see how we go on with that, if that makes it a bit clearer. So let's try another number. I'll move this up, and this time we'll try the number 174. So 174, and that is a decimal. So let's look at the number 174 for a minute. How many? Now it's less than 256, so we're in this second column again. We're in the 16s column. How many 16s are in 174? Well, if we 16 times 10 is 160, and 14 is 174, so we're definitely going to need 10 of these. Now, what is the hexadecimal value or symbol for 10? After 9 comes A, so we would put an A in here, and that would be, and we'll put a hex here so that we know that it's a hexadecimal number, and we're left with 14, and we can write 14 in here. We can't write 14 in here because that's 2 digits. So what is the hexadecimal for 14? Well, 15 is F, so it's E. So AE is 174 in hexadecimal. Now A is 10, and we can represent that in 4 bits as 1010, so that's 8 plus 2. And E, which is 14, can be written as 8 and 8, 4 and a 2. Yeah, so we've got 2 separate 4 bits, and when we put them all together, let's put them all together just for out of curiosity to see what happens. So if we put this together, 1 0 1 0 1 1 1 0, and this is base 2, and if we put the place orders for binary above that, we've got 1 2 4 8 16 32 64 and 128, and we've used 128 plus 32 plus 8 plus 4 plus 2, and what have we got? 120 and 32 is 160, 168, 174. How much more difficult was it to calculate that? That was quite... Whereas by splitting it into 4 bits, A is 10, and the binary for 10, 1010, is quite easy. The important thing is the place order, that you've got them in the right order, remember. This leading bit is called the most significant bit. And it has the highest value, place order value that is, and this one down here at the end is called the least significant bit. Now that's important, because when you are organising yourself and you're organising these bits, the binary, you must start at the right hand side with the least significant bit and split it into 4s this way, so that you don't run into problems. So 1 2 3 4 split, 1 2 3 4 split. Always start at the least significant bit and work up. Okay. So let's have a look at this time converting a hexadecimal number back to decimal, and I think we're going to need an intermediary step of converting it to binary. So let's re-establish the place orders. So 16 to the power 0, 16 to the power 1, and 16 to the power 2. We'll just leave it like that just now. Right, so let's start with a number of, what will we call it? We'll call it 2f. So there's our hexadecimal number, 2f. What is 2f in our world of decimal? Well, the first thing we'll do is we will turn it into binary. So let's get a blue pen for binary. And we've got a 2 here, so we know what a 2 is. In 4 bits, we don't need 8, we don't need 4, we need 2, and we don't need a 1. And f, we know f is the equivalent of 15, so that's 1, 1, 1, 1. So that's us got the binary. And if we add this binary up, and we treat this as 8 bits now rather than 2 separate 4 bits, we've got the 128's column, which is empty, the 64's column, which is empty, but we've got a 32, so I'll do all the workings over here. So we've got 32 plus, we don't have a 16, but we know we've got an 8, we know we've got a 4, we know we've got a 2, and we know we've got a 1. So 38 and 8 is 40, 44, 46, 47. So that equals decimal 47. And I'm going to put base 10 there, just to keep us on track. And I'll put a base 2 there, and I'll put a base 16 there, so that we know what we're doing. Now, how can we check to make sure we're correct? Well, what we could do is we could take the 47 and turn it into hexadecimal, and then we'll know if we're doing it correctly. So over here, we'll start off with our 47, and we'll work out what we did earlier on. How many 16s can we get in 47? So we know 2 16s are 32, and 3 16s are 48. So 48 is too big, so that means we've got 2 16s, so we can put a 2 down. And what have we got left? Well, 2 16s are 32, so 47, take away 32, and we're left with a 5 there and a 1 there. We're left with 15. So that makes sense. And 15 represented in hexadecimal is an F, 2F. Always better to check your workings. So this time what we'll do is we'll convert a binary number. So we'll start off with binary this time instead of starting off with hexadecimal or starting off with decimal. So let's get a binary number. So let's see, what do we want? So it's got to be 8 bits at the moment. So we'll say 1 1 0 1 0 0 1 1. So there's our 8 bits. Let's identify the least significant bit. So here it is here. So that's the least significant. And over here is the most significant. Now that's very important, remember. That's where it can all go hideously wrong if you don't take that into account. When you are splitting your binary number, start at the least. So 1 2 3 4 split, and we've got 1 2 3 4. So we're lucky we've got 2 sets of 4 bits. Right. So what we want to do next is, what is this? This is a 3. And this is an 8 and a 4 and a 1, which is 13. Now, how can we represent 13 in hexadecimal? So 10 is a A, 11 is a B, 12 is a C, 13 is a D. So there we've got D3 in hexadecimal from the binary 1 1 0 1 0 0 1 1. That was pretty painless, I have to say that. Now, how can we check to make sure it's correct? Well, we could work out the hexadecimal and work out the binary and see if they're both the same in decimal. So let's do that. So D is the same as, what did we say that was? D, that was 13, wasn't it? So that's 16 times 13 plus 3. So 16 times 13. Have I got a calculator somewhere? Let me go and get it. do it. So here we have, get rid of that, 16, I don't know if you'll be seeing this, 16 times 13 is 208. So that's 208 plus 3, that equals 211. Right, so that was, let's do the binary now. So it's 11010011. So that's 128 plus 64 plus 16 plus 2 plus 1. So let's get a calculator for this. Clear that. So 128 plus 64 plus 16 plus 2 plus 1, and that is 211. So you know they're correct. You know you have done it correctly because you've checked it by converting the binary to decimal, and you've checked it by converting the hexadecimal to decimal. Good. So let's finish this investigation of hexadecimal off with having a look at when do you see hexadecimal used in the computer? Well, you've probably seen this application in class over your years. It's GIMP. It's the graphic image manipulation program, and if we look at the colour tool, you'll see that HTML notation of any colour, A07188, that should start to make sense to you now. If we go to red, right up to the warmest red, let's see, oh, is that going to allow me to do it? Nearly. I'm trying to get FF. Let me do it. Just type it in here. So FF 0000. I'm going to hit enter on that and look at the colour, bright red. So what we've got here is an RGB colour scheme, red, green and blue. The first two numbers, and you now know they're hexadecimal numbers, are used to represent red. The middle two numbers are used to represent green, and the last two are used to represent blue. So we can test this by if we put FF in the middle here and hit enter, you've got your pure green, and if we take those out and put them at the end, we should end up with a blue. So that should help you to understand that now. Now you see that somewhere else. You hear me going on about this all the time. W3 Schools. Now this is the W3 Schools colour picker, and it's actually called a hex calculator. If you look at the colour tutorials here, there's one called colour hex, and you can see here RGB 25500 gives you pure red, and it's hashtag FF0000, so it's telling you that 255 is the value, and we know that 8 bits can represent 255 if all those bits have a 1 in them. It's very interesting, that, isn't it? So let's look at this. So if we've got FF for red, but if we, this is a colour, this is a, can I drag that? Yeah, FF, look at that, CF, and if I bring that down, so that it's just green now. Or if I bring that down and it's just blue, look at the values. It's changing all the time, so it's 0, 1, 1F, F5. Have a look at that in your own time and become familiar with it and feel confident that you can understand what these hexadecimal colours mean.